Okay, really quick. So we are going to do this example. I'm showing you kind of how you're going to have to look at those, what's happening during a phase change. So this example, 4.7, says how much energy does a refrigerator remove from a 100 grams of water at 20 degrees Celsius to make ice at negative 10 degrees Celsius. Okay, so we're still using our heat equation on this, okay? So we've got Q equals MC delta T. All right, so we've got to use another bit of information. I want you guys to write this down on your PowerPoint somewhere, this table 4.4. You're going to need this table for homework, quizzes, things like that. So make sure that you have this table available. All right, so our mass that we have is 100 grams. What is the specific heat of water at 20 degrees? 20 degrees Celsius. Is 20 degrees Celsius gas, liquid, or solid? It's liquid, right? So that would mean that our specific heat is water. So we've got 1 calorie per gram degree Celsius. And then what's our change of temperature? Some of you might say that you go from 20 to negative 10, so it's 30. Okay, this is the part that kind of is a little different. You just go to the first where the phase change would happen. So if you're going to negative 10, that means you're going backwards on the scale, right? So if we're looking at this, we are about here. We're about 20 degrees. I can't write on the book. We're a little bit over 0. And then we're going to go to negative 10. So we've got to go to 0 first. So 20 minus 0 is just 20. Just stick with me for a minute. I promise it'll kind of come together, at least I hope it does. Okay, so if you take 100 times 1 times 20, you get 2,000 calories. Your grams cancel, your degrees Celsius cancels. Okay? Now here's the next step here. You're going to go to, you're going to go from a liquid to a solid. Okay? So that means that you're fusing it, okay? If you were going from a liquid to a gas, then you would have to use latent heat of vaporization. But since you're going from a solid liquid situation, you have to do this fusion one. So the equation for that, sorry, I keep going back and forth here, is this mass times the latent heat of vaporization, or fusion. Gosh, sorry. Okay, so the mass is still 100 because nothing has changed as far as that is concerned. And your fusion is 80 calories per gram. Okay, so if you take 100 times 80, you get 8,000 calories. Okay, now are you done? No, because you just went to 0 degrees. But now you're finally into the ice situation because this was your phase change. So it took this much energy to go from just the liquid to the solid phase. Okay? Now we got to go for the rest of it. So we still have 100 grams. It's just ice now. And now, what's the specific heat for ice? It's 0.5 calories per gram degrees Celsius. And our change of temperature now is from 0 to negative 10. So basically just 10 degrees. Okay? So now you got to do 100 times 0.5 times 10 degrees. So you end up with 500 calories. And now you just add them up. So your heat is just 2,000 calories plus 8,000 calories plus 500 calories. So you end up with 10,500 calories. Okay, now what if it was like asking you to figure out how many joules that was? How do you do joules from calories? You could do this, right? You could say for every 1 calorie, there's 4.184 joules. Or since you're in the thousands, right? You could say, okay, there's 1,000 calories and 1 kilocalorie. 1 kilocalorie is 4,184 kilojoules. Or, yeah, joules, I guess I should say. Okay, and so you could figure out how many joules based on that as well. I don't think this specific question asked you to do that. I'm just saying that it could. So that might be a thing that happens. Okay, and then, so very last, this is just saying evaporation and condensation. Evaporation, sort of the definition of that is the energy required to overcome the phase cohesion. So cohesion is when those molecules are wanting to stick together. So when they start becoming a gas, like water vapor, then that's the energy that is overcoming cohesion. And it's only happening really on the surface. If you boil water, it just takes everything off the surface, and then the water level continues to go down. Condensation is when actually the gas molecules near the surface lose kinetic energy, and they actually start to go back into the liquid phase. Okay, so you got to know the difference between evaporation and condensation. And then the next part of this chapter is about thermodynamics. The only thing that I really want you to know on thermodynamics is this slide right here. Just what the definition is. It's the study of heat and its relationship with mechanical and other forms of energy. When we talked about it at the very beginning of this chapter, these were sort of the macroscopic, things that we deal with, like heat pumps and heat engines and things like that. So this is saying that thermodynamics includes like systems, so the whole system of that machine, its surroundings, how much energy is coming in, how much energy is going out. Some of that involves friction, which is converting mechanical energy into heat. We looked at that, in the chapter when we were showing how moving something could make heat. Heat engines are devices that convert heat into mechanical energy. And then other things that are used for thermodynamics, like heat pumps, refrigerators, organisms like us, hurricanes, stars, all kinds of things. Now, the first law and all of this stuff of thermodynamics, we're not going to do. So if you have the PowerPoint, you can just kind of cross those out. Those are not going to be on homework or your test or anything, but the main idea of thermodynamics will. Okay, so I'm going to stop the video here, and if you have any questions, let me know. I know that last example was kind of a tricky one, so when we do a review or something, we'll probably do another one or two of that, okay? All right, I will see you guys in the next